All right, this last section of chapter 5 is on the geometric and Poisson probability distributions. The geometric and Poisson probability distributions are two special types of binomial distributions. So let's start with the geometric distribution. So if we have an experiment in which we repeat binomial trials until we have our first success and we stop, this is where our geometric distribution comes into play. So n will be the number of trials on which we get our first success. So in this context, we don't have a fixed number of trials. In fact, n could be any of the numbers 1, 2, 3, and so on. Now, it still means that we have a fixed number of trials, period, but n is not a fixed number. N doesn't represent the number of trials that happen. N represents the number of times that we do the trials until we get our first success, and then we stop. So to find the probability that our first success comes on the nth trial, we use the geometric probability distribution. So here's our geometric probability distribution. P of n equals P times Q to the n minus 1. And again, the probability has to be the same for each trial. That's part of being a binomial distribution. And then we can also figure out what our expected value and standard deviation are. So our expected value is 1 over P. Our standard deviation is the square root of Q over P. And using some simple math, the variance is just Q over P squared. So if you want to calculate the standard deviation and find the variance, just calculate this and square it. If you want to find the variance first and go to the standard deviation, then find the variance and take the square root. But those are your formulas for geometric probability distribution, expected value, variance, and standard deviation. So this is stats from, I believe, this past year, not this year NFL season that just ended, but the season before. Derek Carr ended his season with a passing completion percentage of 68.4%. Find the probability that the next pass that he completes occurs on the third or fourth attempt. Okay, so before we calculate our probabilities, let's find our variables. To find the probability that he completes his next pass on the third or fourth attempt, first find the probability that the next passes he completes will occur on the third, and then on the fourth, and then take the sum. Because remember, they are mutually exclusive events. Okay, so our probability of success is 0.684. Which means our probability of failure is 0.316. And n, we'll use 3. We'll use 3 in the first go-round, and then we'll use 4 in the second go-round. So let's start with P of 3 and then P of 4. So remember, it's P times Q to the n minus 1. So if n is 3, n minus 1 is 2. If n is 4, n minus 1 is 3. So our probability of success is 0.684. Our probability of failure is 0.316. We'll raise that to the n minus 1, so 3 minus 1, which is 2. And I get a value of 0.068. And then if I do the same thing but with a 4 instead, I end up with 0.026. So now I'm going to add those together. That's 0.068 plus 0.026, and I get a probability of 0.094. So about a probability of 9.4%. So again, P times Q to the n minus 1. What's the probability that Derek Carr completes his next pass before his third attempt? Which, in other words, is before either his first or his second attempt. We're going to do the exact same thing that we just did, except we're going to change our values from 3 and 4 to 1 and 2. So when P is 1, I get a value of 0.684. If n is 2, I get a value of 0.216. Now if I add 0.684 to this number, I get a value of 0.900. So I actually have a 90% chance compared to a 9.4% chance of him completing his pass on his first or second attempt as opposed to his third, or fourth attempt. Now, like binomial distributions, you also have a calculator function for PDF and CDF. So for, remember, just like before, PDF represents an exact number, and CDF represents that number or fewer. So in other words, for the previous problem, I'm going to change this real quick. This should be 0.684. And I'll change this here to 0.684. So let's say that we're using the previous example, right? I want to find the probability that Derek Carr completes his next pass on his third attempt. So I'm going to use, I'm going to press second variable. I'm going to scroll down, and I'm going to go past binom PDF and binom CDF until I get to Geomet PDF. And again, it's going to have the menu for you for the later models. If you have an older model, it might require you to actually type in the numbers in the commas. So my P is 0.684, my X value is 3. So this is what it should look like here. I'm going to press enter, and I get 0.068. Now for Geomet CDF, that's to say, well, if I'm doing n less than or equal to 3, that's like saying, what's the probability that Derek Carr will complete his next pass no later than his third attempt? Or what's the probability that he'll complete his next pass before his third attempt? Okay, so that's just another way to interpret a CDF calculation, right? So if I were to do Geomet CDF instead, using the same values, 0.6843, that means he has a 96.8% chance to complete his next pass by either the first, second, or third attempt. Then you have the Poisson probability distribution. So a Poisson distribution is appropriate when the number of trials gets larger and larger, and the probability of successes gets smaller and smaller. So this is named after a mathematician named Simeon Denis Poisson, who studied probabilities of rare events that occur infrequently in space, time, volume, and so forth. So the Poisson distribution applies to accident rates, arrival times, defect rates, bacteria, and many other areas of everyday life. Here is the formula for the Poisson distribution. Here's the formula for the Poisson distribution. I have E, so E is in your calculator. It's approximately equal to this number, E to the negative mu times mu to the R over R factorial. So again, mu is the expected value, and the expected value is given to you, should be given to you during these examples. And so the expected value, turns out, is the same as the variance, right? So the standard deviation is the square root of the average, the expected value, which means that the variance is equal to the expected value. Now, I said this is the rare occasion that the variance and the mean actually are the same thing. Usually that's not the case, but with a Poisson distribution, it is. And to find the standard deviation, you just take the square root of the expected value. But why do we use a Poisson distribution? So again, it's a mathematical model to describe probabilities of arrivals such as cars to a gas station, planes to an airport, calls to a fire station, baby birds, all kinds of things. Now, here's the difference between the two. So the geometric distribution helps you find the number of trials needed to achieve a success. However, the Poisson distribution calculates the number of events that occur in a specific time interval. Okay, but we don't know what that interval is. It could be a large interval or it could be a smaller interval. We don't know. But it calculates the number of successes in that time. Okay, so here's an example. The mean number of accidents per month at a certain intersection is 3. What is the probability that in any given month, 4 accidents will occur at this intersection? Okay, so give me 1 second here. Yeah, we'll get there. I'm going to skip over and go to the calculator because if you want to save yourself some time on the Poisson probability distribution, it's easier to do the calculation instead of the formula. So if you go to your variable, if it's second variables, on your distribution formula, right in between your binomial and your geomet PDF and CDFs, you have Poisson PDF, Poisson CDF. And again, it's the same values as before. The probability that R is exactly that number, that's your PDF calculation. The probability that R is less than or equal to a specific number, that is your CDF population. Okay, let's go back to our first example. Here, our mean, our expected value is 3. Our R, we want the probability that in any given month, 4 accidents will occur. So our R is going to be 4. So 4, 3. So that means that I'm going to do a Poisson PDF where my expected value, so it gives you the Greek letter lambda, but we're going to use, but in this case, we'll say that these two are the same. We're going to assume that those two things are the same, okay? We'll type in the mean. My x value will be 4. We'll paste that on there. It should look like this. We got a probability of 0.168. 0.168. Here's another example. The average number of oil tankers at a port city is 8 per day. Find the probability that the number of oil tankers on any given day is exactly 8. So in this case, our R and our average are the same. So again, that's a Poisson CDF calculation of 8 and 8. That gives me a probability of 0.140. Now, a local fire station receives an average of 1.2 rescue calls per day. Use the Poisson distribution to find the probability that on a randomly selected day, the fire station will receive 3 or less calls. So here, my R is going to be 3. My average is going to be 1.24. But this time, I'm doing P of R being less than or equal to 3. That's a Poisson CDF. So instead of Poisson PDF, I'm going to go down to Poisson CDF right here. Enter. My average is 1.24. My X value is 3. This is what it should look like. I'm going to press enter. I get a value of 0.963. We've already done this. Now, another useful tool for Poisson distributions is to approximate a binomial distribution. So the only way that this can happen is if the value of n is large enough and the expected value is small enough. And so what you have to look for is these two things. You want your n to be larger or to be at least 100. It can be 100, but it can also be greater than 100. And the expected value has to be less than 10. Then you can use a Poisson distribution to approximate the binomial distribution, okay? So remember, n has to be greater than or equal to 100. The expected value has to be less than 10. Here's an example. Isabel Briggs-Myers was a pioneer in the study of personality types. Today, the Myers-Briggs type indicator is used in many career counseling programs, as well as in many industrial settings where people must work closely together as a team. 16 personality types are discussed in detail in her book by Myers and Macaulay. Each personality type has its own special contribution in any group activity. One of the more rare types is INFJ, introverted, intuitive, feeling, and judgmental, which occurs in only 2.1% of the population. Suppose a high school graduating class has 167 students, and suppose we call a success the event that a student is of personality type INFJ. So is a Poisson distribution a good approximation? Well, look at the n. It's greater than 100. Look at the p. It's 0.021. I need to find the expected value. Expected value for a binomial distribution is n times p. So that's 167 times 0.021, which is 167 times 0.021. That's 3.507, which is obviously smaller than 10. So yes, a Poisson distribution is a good approximation to that binomial distribution. Estimate the probability that no more than 4 people have the INFJ personality type. Estimate the probability that at least 5 people have the INFJ personality type. So we want, for part B, we want the probability of R being less than or equal to 4. And here we want the probability of R being greater than or equal to 5. Well, let's go ahead and let's use our Poisson distribution, okay? So we're going to estimate, so we're going to go second variable. We're going to go to Poisson CDF. Our average is, what was our average? It was 3.507. Our X value is 4. Okay, so this is what it should look like. And I end up with 0.724. Now to find the probability that at least 5 people have that, that's the complement of the previous one. So I'm going to take 1 minus 7.724. And I end up with 0.276. So as long as n is greater than or equal to 100 and our expected value is less than 10, you can use a Poisson distribution. You can use a Poisson distribution to do this, to estimate the binomial distribution. Booyah!